let's the fun begin. Sliding mode control, right? So what we will, I'll kind of motivate the problem. So motivating example.
It's still chapter 5.
No, it's chapter 14, I believe.
Oh.
So, but it's in the notes. Sliding mode is chapter 14. Okay, nonlinear design tools. So we kind of have enough tools to understand this concept. Okay, so let's see. So x1 dot equals to h was chapter 14. Okay, but mostly notes will be a good place to start. So x2 dot equals to h of x plus g of x u. Can we reduce some volume, Anand? Let me know when you're done. We can daddy can eat it if you want. No? Okay. So so we have to design a control, like mostly the controls will be like going to the origin, right? So that's the thing, like can we go x, right? X equals to 0. That's the origin, right? So but the problem is h of x and g of x are unknown. Right? So I kind of, so that's the issue here. You want to design a controller, you want to find an u such that x goes to 0. That is the control objective, right? But what is the issue? H of x and g of x is not known to you. That is the challenge that you have to overcome while designing this problem. And let's see how the tools that we have used so far can be helpful here. Okay? But we know something about these things. For example, g of x is, lower bounded by g0, for example. Okay? So what is the step 1 of this problem thing, right? So this g of x has a bound, is always lower bounded by g of 0. So this quantity is 1. We'll go to the theory later on, but let me just propose the problem. Step 1 is choose a sliding manifold. Okay, we call it manifold because right now we are doing a scalar 2-dimensional problem, but it can be a larger problem, so it can be a manifold. Okay, so let s equals to a1 x1 plus x2 equals to 0. Let's say this is my sliding manifold, and if you see, what is this right now, at least in this is a equation of a line, right? This is the equation of a straight line, right? Y equals, so if you see, x2 equals to minus a1 x1, right? So it's a kind of a line equation. In fact, line passing through the origin, isn't it? It's a line passing through the origin whose slope is a1, basically negative over a1. Right? So basically, if this x1 increases, things decreases. So will it be this? So if x1 increases, y decreases. So this should be like this, right? Something like this. So this is a line here. This is s equals to 0 line. Right? So the idea is to, first you choose this manifold. So basically the slope determines how fast you converge to the origin and all that jazz, right? So that's the manifold you have. So the idea is, if you are anywhere here, you basically push the system to this, and then this basically slides to the manifold. So you can ask why do you think that if when we are on this we will slide to 0?
So let me ask this first.
Mhm.
For when there's just an x1 and x2,
Mhm.
you always assume S equals, is that always your manifold you're selected for two states?
Yeah.
Okay.
So we will see how you choose it. Like you'll get a clear idea why we chose this.
Okay.
Will be clear as we prove that when you are on the manifold, it means you are on the you are asymptotically stable.
Okay.
Next
Like for
one.
example, like when we could choose any what was v of x, that candidate function.
Mhm.
You could choose any one, and we just kind of mostly always choose 1/2 x1 squared
Yeah.
plus. Like that's
So-
your go-to. If
yeah.
that doesn't work,
So
then you can-
in a
is that the
two-dimension,
same
yeah,
thing?
in two-dimensional case, it will
You can
be a
pretty much
line.
just pick that one. Okay.
Yeah, it's
Okay.
a line.
Okay.
Yep.
Okay.
You'll see that in two-dimensional case, this is the case. So, for example, at s equals to 0, how can I write? I can write x2 equals to a1 x1, right?
Okay.
And now if a1 x1, so if I choose like v equals to half, what x1 dot equals to x2 dot equals to hx plus gx u, right? That's the kind of thing. So let's say I choose a candidate function half x1 squared. What is that? V v dot equals to x1 dot, right?
Yeah.
Which is equal to x1 x2. And what is x2 right now? If you manifold. I'm dealing with, so this is assumption that you are already on the manifold. So that means s equals to 0, and that means x2 equals to minus a1 x1. And when you plug this in here, it becomes minus a x1 squared. What does that mean? That means if you are at the manifold, x1 goes to 0 for sure, right? Because v dot is negative definite, right? V dot is minus a1 x1 squared. So that means x1 definitely goes to 0 if you are on this manifold. And when x1 goes to 0, because s is 0 on the manifold, x2 also goes to 0. So that means if you are on the manifold, system is asymptotically stable.
So is half x1 squared.
Yeah, just half x. I just chose v equals to half x1 squared. See, you're not worried about x2 right now. You're saying, can I show from here, if you only have one state, if you are on that manifold, will x1 go to 0? So that goes to 0, and if in doing so, because you are on the manifold, this condition, your x2 also goes to 0 if you are on there. So you basically slide down to the origin. Okay. So now the idea is to push with even these given uncertainties of gx and hx. So you don't know this, right? You don't know this exactly. You don't exactly know this. How can we push the system to this manifold, and then manifold will take care of itself? So that's the idea. That's the basic concept.
Not when it's in Z, it doesn't suggest that we don't know the model itself.
Yeah, that's what we mean. That's exactly the thing. You don't exactly know. You don't know more. For example, you have an inverted pendulum, right? Let's say somebody just gave you the stick and you don't know the length of it. You know that by just eye you can inspect and say, hey, it cannot be more than 2 meters, I think, or maybe cannot. So you know the rough upper and lower bounds of the system, but don't exactly know its limits. So yeah, let's see how that will play, right? So that means if you are on the manifold, are you done? Can we throw it? No? Right, so first page here that is. Now let's see. So that's step 1. That's our choosing the sliding manifold, appropriate sliding manifold. So the criteria for choosing the manifold has to be this: that both x1 and x2 has to go to 0. You should be able to show that on that manifold. That is the So now,
Do you pick the sliding, like the manifold, based on how you can control
yes,
it?
from this, yeah, based on showing that, can I show that x1 and x2 equal to 0?
But is the manifold based on like your control, like how you're actually controlling
No,
it?
no, no, not
You just
not all.
pick it
You
the
pick
same
it
as
how nicely. So if I have bigger slope, like if I choose now, A1 is in your hand, right? I can choose A1. Whether A1 is like this or like very flat, or how fast you want that manifold to be, or how as soon as you go, how fast you want your solution to go to. That's the design choice. That's what you will have. That A1 will be come in your equation. So your controller will be a function of S now. You see this S, your controller will be a function of this S. So yes, controller eventually will be function of this sliding
I
wheel.
see.
Okay. So now, so step 2 will be, so once having decided what the manifold is, which is S equals to A1 x1 plus x2, right? Equals to 0. So on the manifold, you are S equals to 0, but now we want, if you are outside the manifold, S is not 0, right? So basically you want your control effort to make that S 0. That is the objective now. So let's say, so outside the line we are not 0, that means A1 x1 plus. Anand, let me know if you're done. So now let's choose a candidate function called half S squared. Because see, now I'm interested in taking S equals to 0. Right? If I can show that my V dot for this candidate function, new Lyapunov candidate function, half S squared, if I can take S equals to 0 somehow, then we're good, right? So let's see. So what is S dot from here? So S dot will be A1 x2 plus x2 dot, right? And x2 dot, if you remember, is h of x plus g of x u. Okay? So that's here. So if we say V equals to S into S dot, right? V dot S into S dot is A1 x2 plus x2 dot, which is h of x plus g of x u, right? So so if we do that, then now what we can do is we can divide the whole thing, because now by g of x, so we can take g of x outside, s of g of x, a1 x2 plus h of x, right, over g of x plus u. Okay. Now let's say that you don't exactly know h of x, g of x, but you can use those, it's some details of upper bounds and lower bounds to compute a upper bound on this quantity. Okay. So let's say the mod of, let's say we are defining it, we are saying a1 x2 plus h of x over g of x is less than equal to some rho of x. We'll see when we do the example. So it's an upper bound. That your this function, right? This function cannot be bigger than this. That is the idea here. Like no exact details needed. Like what exactly? I'm saying that depending on some knowledge of the g of x and h of x, length of a rod or whatever, you put this rho f x in it, right? So we can use this now to so we can write now, we can write this equation again as v dot is less than equal to g of x taking a modulus of s into rho x, upper bound of this, right, into su. Okay, right now let's just write like this, right? So this is g of x is outside and this. Okay. So now question is, what is my objective here? I want my V dot to be negative definite. So now this function is given, so now I have to choose U now. What should be my U such that this whole quantity becomes negative definite? That is the question we are asking. So what if, see, what I want to do is I want to cancel this term out. So what if I choose this, U equals to minus some beta x into sine of S. See, when I multiply sine of S into S, it becomes absolute value of S, right? What is mod of S? Mod of S can be written as sine of S into S. So sine S will be either negative or positive, right? But let's say this is positive, then it will be positive. If it is negative, then it will be negative. So negative. So this always. So if I choose this, so that's the idea here. And if I choose my beta x is some rho x and plus beta x equals to rho x plus some rho 0, some positive value or something, some rho 0, right? So if you plug this in here, what happens? It becomes g of x rho x sine of S into this. So we are plugging this into sine of S, right? So this becomes mod of S rho x plus rho 0. You can close the door if you want. इसको इधर से क्लीन कर देते हैं. Check. I can throw it if you don't like it now. Can I throw it? Can I throw it? Enough ice cream, Euro. If Mama finds out, we will be in trouble. Okay, so now you see, so this was negative of it, right? So it becomes negative here. See, sine of S into S is mod of S multiplied by this term, right? So you see now this cancels out, this cancels out. So the remaining part is minus g of x rho 0 into absolute value. So what is this? Rho 0 is positive. This you see that we already know from top negative. So what is where is your controller? This. So this controller u equals to minus beta x. Beta x is nothing but rho x plus rho 0 into sine of s brings what does it do? It makes s go to 0. Right? That's all we are doing. We don't know h of x, g of x exactly, but this controller will make s equals to 0. What does that mean? So it puts, doesn't matter where you are, it puts you on this. Once you put on this, you go slide to the origin. So that's the basic objective. That is the main kind of fundamental thing that. And let's throw it. Okay, enough. आपने खा ली? नहीं. Enough. Sorry guys. लो पानी पी लो. Okay, so you got the idea, basic idea. So this controller, see how, what kind of controller is this? I'm just saying, if you are this side or this side, depending on the sign, it's a bang kind of controller. It is either it goes with full force. It goes with full force of this into positive value or negative value, depending on which side of the manifold you are. If this side is considered positive, then you go this side with full force. If you're here, you go full side. It's kind of, because of let's say not exactly, there is some kind of momentum. It overshoots it then comes back. Overshoots, come back, and then kind of. So you will see that pet nature of bang bang type of control. So you just imagine u equals to minus kx to u equals to minus beta x of sine of s is the control. So without even knowing exactly the plant or the model, we are able to put and design a controller, just a very simple, this is like very basic controller, right? A sine of s. So if you have this side, go positive this side until s is to 0. And then on manifold, it's guaranteed that you will reach your. So this is sliding mode controller. There are two phases. One is sliding phase, one is reaching phase. Right? So this is reaching phase. You reach here and then you slide. So reaching phase versus sliding phase. Okay? So that's the basic idea of this controller. And you will see, like, we can put this on the inverted pendulum and see, I don't know the length of it or exact mass of it, but I know that the mass can be between this and this value, the length can be between this and this value. Still, you will see that the pendulum will go in one shot like this and then do this and then that's the beauty of this. When with plant uncertainties and all, you can design a controller where it's reaching phase and sliding phase. Okay? Got it? So the picture looks something like this, like if I were to draw it here. So this is what I'm interested in, right? This row of x. This is what I'm interested in, because if I can put into this same form, and because, right? And then try to compute this row of x from there, right? So that's our, okay, so that's, let's say I choose my sliding manifold to be this, that is, so, right? So that my s equals to 0, and the basic thing is coming from, so if you are here, you go there. If you are here, you go there. If you are here, you go there. Something like that. So kind of, okay. So this is reaching phase, and this is sliding phase, kind of a picture. Okay, so so now that S, the choice of A1 was your design parameter, how fast you want to slide. Okay, and in fact you can show that you've reached here in finite time. I can do some math and show you that it will reach in finite time, and then. But there is an issue here, because see, what are we doing here? We are doing non-feedback linearization, right? We are cancelling some terms. I'm using U to cancel the maximum of that row of x, right? But there will be noise, there will be time delays in real systems. What will happen? Because of that, you will overshoot this thing. When you overshoot, it will again, from maximum force in the opposite side. As soon as you change sides, it becomes negative, right? S becomes negative, and your control direction changes. So you will go here. So you will see in real-time system, you will see chattering. So that's called chattering. How do you avoid that chattering? So because this is a discontinuous function, because of that, you will see, I'll show you actually in simulations that there is a lot of chattering. And how do you avoid that chattering? Because even in MATLAB, it is solving an ODE. ODE solutions are all approximate. And approximate solutions, you will say that because of the numerical errors, it will overshoot, and it will do, you will see high frequency chattering because of that. So then instead of sine function, you can use saturation function. And you will see it kind of compromises something, but it will remain more continuous, at least near that case. So I'll show you mathematically how that works. But so any questions on this?
There are methods to find the optimum value of A.
No, that's, I think that is like a design, your design challenge, that what you want, like when you choose A, whether it is fast, smooth, how fast you want to reach the origin, that kind of thing. So it's a design parameter. There is, I'm sure A will have some effect on how quickly you reach to the origin, and that will depend on the problem. So it's kind of a gain. In a control, gains like until unless you are saying that for this quantity I want to minimize this energy and this energy, and so the question can come, what do you want to optimize, how do you want to find that. So A is a design parameter that you can choose depending on the problem, how quickly you want to go to. Because yeah, sometimes when A is too small, it can take forever to reach there. Okay? So we'll do the math. Means I will in the next class we'll do all this math, that how this reaches in finite time and all that jazz. But let's do an example of pendulum, and then actually you use MATLAB to show that how that works. Okay? Page. So inverted pendulum example, x1 dot equals to x2. So inverted pendulum. Okay. So inverted pendulum is x2 dot equals to minus g by L sine of x1 plus delta minus k0 by m x2 plus 1 by ml square u. See, this delta is added because I want pendulum to be at an angle delta rather than 0. So you can change your equilibrium point. Okay, so so let's say this is the equations of motion. So you will see that you can treat this as h of x, right? And this as g of x. Right? If you see in your inverted pendulum example. So now the idea is like putting into that form. So basically what I want to do is find so if you remember our equations from so let's choose our s equals to, again same, a1 x1 plus x2 equals to 0. That's your sliding manifold. And then our, if you remember, so yeah, so x2 equals to minus a1 x1, and you can show that v half x1 squared is negative definite and all that. So we already know that because it's a general same form, right? So basically if you see the controller, we have to find this rho of x, right? So if you go to the previous, so rho of x equals to a1 x, what was that, a1 x2, right, plus this plus h of x over g of x. So this is h of x and this is g of x. Okay, so we want to find hey Anand, what are you doing? Hey bandar, monkey. So right. No, so we want to find an upper bound on this quantity, right? So we can take an absolute value of these things. So we can write so let's plug in the values, all the values. So we have ml squared So if you see g of x is what? 1 over ml square, right? So 1 over gx will be ml squared. So ml squared multiplied by a1x2 plus h of x, and plus h of x is ml square, so into what was that, m,
Looks like negative G over L
so negative g over l
sine.
sine of x 1 plus delta minus k0 by m x2. Okay, so now let's multiply this thing. So m of l square, ml squared a1 x2 minus gm l sine of x 1 plus delta minus k0 l squared, right? M will cancel out, so x2, right? So this quantity now now we can say, so this and this same, right? We can have x2 is outside, or we can take x2 outside. So this is l squared ma1 minus k0 l squared, right, into x2 minus mg l sine of x 1 plus delta, right?
Do you need that this term? Since you already got it here?
Yeah, we don't need this, right? So exactly.
What? Well.
No.
You,
Yeah, I don't need this here.
Right. Yeah.
L squared, exactly. So it is L squared ma1 minus k0 x2 minus mg L sine of x1 plus delta. Okay. So now, if we can say finding out this can be less than, we can apply the triangular inequality, right? We are taking absolute values. So a plus b is less than, so like a minus b is less than equal to a plus b, right? So, so L square, absolute value of, L square is always positive, so not a problem. ma1 minus k0 x2 norm plus mg0 L. Maximum value of sine will be what? 1. I'm just, because finding upper bound, right? I'm saying what can be the maximum thing for this and what can be 1. So that's m0 L, right? So we can, let's say if you say pick, if I pick a1 equals to 1, the slope of 1, that means 45 degrees of slope, right? So we can, that's in my hand, right? And I can choose my x2.
So this, that ma1 minus k naught, is that in the absolute value, or is that
Yeah, you can.
parentheses? Which
Yeah,
one?
yeah, right now I'm using parentheses, but you can have an absolute. We will also get
So
a
that does also
bigger.
positive.
Yeah. As long as we can.
Okay, so is k naught always positive? So m's mass always positive. What's k naught?
K naught is
Physically?
the spring
So
constant.
that's always positive?
Yeah, that is always positive, but we don't know the values, so we'll that's what now we will do.
Oh, okay.
Is apply their values. Can I get the book? I think there's some values given there.
So we don't have a relationship to k naught to mass.
So let's say x2, right? x2 is what? x2 is theta dot. It is the rate at which theta changes. So let's assume that x2, mode of x2 is maximum can be yeah, it can be on the right page. So that can be 2 pi. So I'm saying that x2, the absolute of value of x2 is less than equal to 2 pi. Just like the rate, you're fixing that it cannot, and it's, yeah, like if it's starting from 0, the rate cannot be more than 2 pi per second. So that's the upper bound you're putting on it. So when you do that, you can come with, so, and this is given to you, for example, x1 cannot be greater than pi also, right? Because 0 to 180 degree. Your x theta has to be between 0 and pi, so maximum value for x1 is pi. So this is given to us, like your mass is between 0.2 to 0.05. This is given to you, like you don't exactly know the mass of the ball, but it's saying between this, and you don't exactly know the length of the rod, and it is 1.1 to 0.9, and you don't exactly know the K, spring constant, which is given to K0 0.05 to 0. Okay, so these three things are given to us, and we have to apply it here to give the maximum bound for this. So so gravity, everybody knows G is 9.8, right? So to maximize this quantity, we can take the maximum value of M, right? What is that? 0.2, 9.8, something like around, so 9.8, and maximum value of L, right, is 1.1. So that's fixed here. To maximize this, right? So this is L. So again, so I can take A is 1. So I can take, you have to take K0 minimum and M maximum, right, to maximize it. And K1 is 1. So what will be that value? So it is 2 pi. What is L square is 1.1 squared. And M, what is M? Maximum value is 0.2, and K0 is, so that will be, what is that? 0.2 minus 0.005. So that's the thing, 1.1 squared, 0.2 minus 0.005, because now it stays positive, right, into 2 pi, plus 0.2 into 0.98, 9.8 into 1.1.
But you said to maximize that MA minus K0, you said pick the maximum mass and the minimum
Of K,
K0?
yep. That's how you maximize that.
Wouldn't it be 0 then, not 0.05?
Yeah, sorry, 0. Exactly. So that's 0.2, right? So if you do this math, it comes out, this will be equal to 3.68. This whole thing. If you just multiply things, 3.68. Okay? So this is your row of x. So if you remember, we were choosing our v dot for, if we want to make half s square, s go to 0, v dot was less than equal to g of x into mod of row of x into mod of s minus of row of x plus beta 0 sine of s into s, right? So this is again absolute value s. So we have to choose. So this is 3.68, right? No, maximum value is 3.68. So what if I choose this whole quantity to be 4? Right? So beta 0 will be what? If this is 3.68, beta 0 will be 0.02, yeah, means 0.32 something. Right? So 0.32. So yeah, beta 0 is 0.32 and rho x is this. So my my u will be minus of 4 into sine SIGN of S. That's your controller. What is S? x1 plus x2 basically, because a1 is 1.
You just arbitrarily pick 4. That's what you did as a designer.
Yeah, just a little bit more than, so there was 3.68, I need to choose at least something greater than this one. So I just chose 4. It has to be more than 3.68 to cancel out that row of x, right? So I chose 4. You can choose, yeah. it will
Okay,
work.
because you're subtracting it from.
Yeah.
Yeah.
So I have to choose something more than that 3.68. But you see that's the simplicity of this controller. Minus 4, plus minus 4 basically. Plus minus 4 of S. Because this is sine, right? So it what is the exact value of S doesn't matter. Only S, the sign of S matters. So what is the control? Minus 4, plus 4, minus 4, plus 4. Simple. That is the simplicity of the controller. We're just saying apply minus 4 or plus 4 depending on the sign of S, and your pendulum will be. Let's see it before I think we can.
But so the value of S will decrease to below 0. So it never actually diverges to 0. Then that chatter will stay. The magnitude of that chatter will stay the same.
No, chatter will not stay same because every time you go, you're close.
So S does get closer and closer to 0. S.
Yeah, because that's what you showed right here.
Okay, that's what step 1 is, finding that modulus.
No. But V dot here makes it V dot negative definite.
Okay.
Which means S is going to 0. Even with minus 4 plus 4, your S is going to 0. See, what you do is when you are here, for example, where is my... Where did I keep my... Here. So, see, we are showing that your V dot is negative definite, right? Is less than minus beta 0 S. This is what I'm showing, right? So that means V goes to 0 eventually and S goes to 0 eventually. So even with this minus 4 plus 4, right? So you immediately, as soon as you will cross, the sign will change. So you will with full force you will come here. So that thing will die down.
I guess it will. Okay, that's what I'm. Okay.
Yeah. So see, I'm starting for the first time, plus as long as you are in this side plus 4 plus 4 plus 4 plus 4, and as soon as you touch it, ideally you should have remained on that.
Right.
And S goes, but you overshoot it. As soon as you overshoot it, your sign changed. And here, as soon as you go, so this pretty soon it should die down.
That's what I'm
ideally.
asking. Okay.
Yes,
So even applying plus or minus 4, it does
Yeah,
die down.
because
It's not
of-
like you're
because of this
applying less
mathematical-
than plus or minus 4 every time.
Hmm?
Because it's not like you're going like if you go negative 4 plus 4, but I just wanted to make sure it still
Yeah,
dies
control
down
is still
because-
minus 4 plus 4.
Okay.
But your S,
Okay. That's
because
what I'm asking. All right.
how long you apply that minus 4 is a different thing, right? Here I'm applying minus 4 plus 4 for a longer time.
Okay. Okay.
As soon as you cross, it becomes minus 4 and you apply minus 4 until you cross this.
Right.
But that time for which you apply minus 4
Okay.
changes.
Okay.
But now I have to apply for the first time you have to apply plus 4 for a longer time. And suddenly as soon as you cross that line, immediately, like if you're continuous, immediately you will be pushed back. So yes, S definitely will. And mathematically, right? I know that it's negative definite, so S has to go to 0. That's in the first place we designed the controller for. So the control is simple, minus 4 plus 4. When do you choose is depends on the sign of the S, but this takes S to 0 and then eventually you go there. So let's see. I should have a simulation somewhere. So it's the same inverted pendulum simulation, right? So we have been doing. that's my. You will see a card, but card is not necessary. I was feeling lazy to change the. So this is there now. If you see my controller, right, sliding mode controller. Means I have other later things on to do, but this U1 is minus K into sine of S. Simple as that, right? And K is this. Okay, so we can all output is U1, right? So let's just and then shift. Okay. So this is my controller. U1 is minus 4 of sine of S. As simple as that. And so let's see if we can run this pendulum. Okay, so this pendulum. So same thing, pendulum equations are there. You're just putting U equals to minus 4. Minus 4 of sine S. Sliding mode, manifold, and then maybe mirror displays. Let's run again just for the sake. I'll show you all the graphs like chattering and all, but dismiss all. Right, so one more time. So it goes down from here. Some
So all
like
that
even that linearization and everything is not needed because I'm just even from the down. So if we see the plot of controller now, so it becomes really slow because now it's sliding, but this is x1 and x2 plot. You will see that, and then here. So I think this is the sliding manifold. Once you got here, it kind of slide it. But let's see
it
that.
just overshot right there. Didn't it?
And now it might have overshot. But let's see the control. Do I have a control somewhere? Yeah, here, right? This should be. This is U. So U is between, you can see minus 4 to plus 4. So it does. So initially it get what, maybe it has get minus 4 and then eventually. So this is whole sliding manifold, I think. That x equals to minus 1 line, right? This is manifold. So it might have gone from here to there and then. So we can change points and see what happens, but then it is basically trying to keep it on the manifold. As soon as you get out of the manifold, it pushes it using minus 4 plus 4. No, it's not. So let's choose different. And then what happened? So where is my param file? So it goes from pi to pi, so let's make them 0, 0. Not 0, let's say pi by 4 to 0.
how can you make it aggressive? You can change A.
Yeah, you can change A. You can change, like I chose beta to be 0.32, right? I chose -4, you can choose -5, -6, -10. But you will see the chattering will be more. This is not a good, it will burn down your motors. So next time if you use like a saturation function, I'll show you, it will make things continuous. In fact, I can show you right now, but we can come back and do the mathematical analysis later. This kind of control, like within 0.5 seconds, if you have done this -4 + 4 -4, your motors will burn. Even though mathematically it is bringing things to zero,
Right.
this is not a good controller from that perspective. So if you see, right now if we go to controller, and we'll do the math next time, just let me show you, like if U2 is a different controller, same thing. So if you, I'm using, instead of sine, I'm using a saturation function inside this, and let's see what happens then. So if you go from here, if you see there will be no chattering as such. There is a graph here. So this was the reaching phase. See, you can see clearly the reaching phase, and then it is just sliding to the origin. Came here and then it is sliding through here. And if you see this, not this. See how the control -1 to 1, and then this. So the nature of the control changes. Like if you instead of you go from sine to saturation, and I will show you the mathematically it makes sense, and it's not like you cannot take exactly to the origin, but you can take it area close to that, but with a much smoother control. So we'll do this math in the next. I would suggest you guys read it.
Alright, so I guess what I'm confused about, what I expected to see, and explain to me what I'm missing conceptually. Okay, so you got your pendulum here, and it comes around this way, okay? This whole time, it's the controller is going +or -4.
No. Plus.
See, I didn't expect it to switch sides until it got.
Yeah, exactly.
equilibrium
That is what is
point.
happening. This is exactly what is happening.
But that's not. I didn't think that's what I was saying. Why was it
In
still
the first one,
zigzagging?
maybe
Yeah,
it
in
says-
the first one, I didn't expect.
In the
that.
first, so this is why. Until this, it is using one sign of the controller.
That's what right, and then only when it gets close to
Yep.
0 does it switch.
But I
back
think
and
there the
forth.
saturation where it started, right? So we started somewhere very close to the manifold, so you were not able to see.
And then, I'm talking about the first example.
Yeah, the first example. It kind of died down. It kind of, the chattering's magnitude was so large that this kind of was hidden
Okay.
in that.
Okay.
But yeah,
Okay.
this is exactly.
Because
what is
basically
happening.
I expected to see either +or -4,
Yeah.
but constant the whole
Yeah.
time, and then once it gets to the equilibrium point, overshoots the equilibrium point,
Mhm.
is when the sign change
Exactly.
occurs.
That's
Okay, I
exactly
just
what
didn't think
happened.
that's what I saw though.
No.
Okay.
It was happening because it kind of,
Okay.
the chattering amounts was that much that it kind of overshadowed that
Okay.
reaching phase.
Okay.
Exactly, that is exactly what is happening.
Okay.
So yeah, I can put this code.
And so even when you put up the controller though, I expected to see a whole +4, +5 line.
No, in this
and then
case,
switch.
yeah.
Go back and forth, but that's not what you showed the first time, is it?
Yeah, let's switch, because I think what is happening there is it is somehow overshadowing that.
Okay. So constant, and then when it gets vertical is when you should see a sign change. So we're talking seconds here, where it should be a constant value.
This here,
Okay,
then once it reaches here,
so it's just not reaching though here. Now I should start seeing zigzagging, right?
yeah. So once it already no, it's the sliding manifold is not. You're confusing the zero position with the sliding manifold.
Okay, that's probably right then, okay.
Yeah. So So this is the position where it entered the manifold, right? See, manifold is x1
Okay.
plus x2 equals to 0.
Okay,
So the place where x1 equals to minus x2 is the
Okay.
manifold, not
okay,
the
understood,
the
okay,
top
that's
point.
what I'm missing conceptually, okay,
It's a line, straight line,
Okay.
rather than a point. You were thinking it goes here and then it does
yeah,
that.
that's
No,
what, that's
no.
exactly what I
No, no,
expected
so
to see, okay.
it goes to a position where both are equal.
Okay.
And from that point on,
And use the plus or minus 4 to
uh,
bring it to the equilibrium.
Yep.
Okay, okay,
So now you see
okay.
this, if we plot. So it's so clouded right now,
Yeah,
but if you
yeah.
see,
I think I understand now, I get what I was missing, it's just.
yeah, so it does till 0.02 second, it only
Okay,
applied,
Okay,
right? After that it was.
got it, okay.
So because it reached within that immediately
Gotcha.
0.2 second it reached, and then it.
Okay,
So again, that manifold is x1 equals to minus x2. So as soon as both these, the x1 was equal to minus x2, then it kind of slided.
okay.
So it's pretty cool, like the way it works. Like, because the math is there, supporting is that, the v dot is negative definite, that means s will definitely go to 0. Huh? And then, because at sliding manifold, x1, the v dot is again negative definite, it will definitely slide to 0. So, kind of guarantee things.
Considering the efficiency, I think it's not that efficient.
Yeah, no, but as I said, you can use saturation function after. So we have to. So this is the starting, right? So we'll spend a week on this sliding manifold. So I gave you another version of it, right? Which was very smooth. So it's not important. Like, is it really important for you to really hold 90-degree vertical, or 89.8 is okay, and you can achieve that in a much smoother controller. So that's the kind of thing. And we can even guarantee how close you will reach to the origin. So we will use all our boundedness and input state stability kind of concepts here to show. So that's amazing. Like, what I think when I first time did it, that wowed me. Like, wow, how can this happen? Like -4 until you reach, and then it's very simple. Implementation wise, it's a very simple controller. And mathematically also it is giving you proof. And then we improve on the
It's
performance
not
by
work.
using saturation function or something. Right, Anant? You got? Oops.